This video is all about problem solving with exponential equations and exponential functions. We're going to avoid logarithms for the moment and use technology. Problem 1 involves two exponential functions, f of t and g of t, and multiple parts for each function. So I'm going to split my paper into two pieces here. This column over here is going to be for f of t, and this column over here is going to be for g of t. We've got multiple questions to answer for each part. How do we know these are exponential functions, first of all? It's because the variable, the independent variable, t, is in the exponent. It's the exponent of 0.97 up here, and it is a multiplier of the exponent in this function here. The base is the special number e, which is about 2.71828. That's what makes these things exponential functions. Take it step by step. Part A will do for both f of t and g of t. The question is it growth or decay? The key thing to look at is the base, the 0.97 in this case, for the f of t. That's less than 1. That means this is exponential decay. If it were greater than 1, then it would be exponential growth. So for f of t, part A, this is decay. If it equals 1, then you get 1 to the t, which is always 1, and it's not really an exponential function anyway. So we want either something between 0 and 1 for decay or bigger than 1 for growth. For this form, where the base is e and we have an exponent that involves some number times t, that number, that coefficient, when it is positive, means this represents exponential growth. If it had been negative, then it would have been represented exponential decay. On to part B. What is the initial quantity? The initial quantity is the function value at 0. When you plug in 0 here into this formula, you get 0.97 to the 0 power. The power is done first order of operations wise before multiplication. Anything to the 0 power, except 0, is 1. So we get 8.3 times 1 when we plug in t equals 0. That gives 8.3. The initial amount for f of t is 8.3. What about for g of t? Plug in 0 there, you get e to the 0, which is 1. 4.6 times 1 is 4.6. So the coefficient that's in front in both cases is the initial quantity. G of 0 is 4.6. Part C. What is the change factor per unit time? What in the world does that mean? The change factor per unit time is the amount by which, it's the multiplier by which the function grows or decays as t, in this case, increases by 1 unit. Let's try some numbers. So for example, with f of t, we start off with a value of 8.3 when t is 0. What is the function value when t is 1? It would be 0.97 to the first power, 0.97 times 8.3. You've got to multiply 8.3 times 0.97 to get the next value at t equals 1. When t equals 2, you'd be doing 0.97 to the second power times 8.3. You can get that by multiplying by 0.97 again. 0.97 gets multiplied again to get the next value when t equals 2, 7.80947. The change factor in this case for the function f of t is the 0.97. That is the change factor. What about for the function g of t? Again, you're thinking about what happens as t increases by 1 unit at a time. When t is 0, again, you get 4.6 times 1, which is 4.6. To get the next value when t is 1, you need to multiply 4.6 by e to the 0.03 times 1 power, which is e to the 0.03. E to the 0.03, if I multiply by that, I get the next value at t equals 1. In other words, e to the 0.03, which is a little bit bigger than 1, is the change factor per unit time, about 1.03045. Approximately 1.03045. Okay? That's what you're going to get. When t is 2, you'd multiply by e to the 0.03 again. It's the change factor per unit time. Part D. What is the relative rate of change per unit time? I put the word percent in there to emphasize that you typically do think of it as a percent. All right, this is a little tricky as well. You got to know your terminology. This is exponential decay. The change factor, 0.97, is less than 1. As t increases, the values go down. The relative percent rate of change has to be a negative quantity in this case for the function f of t. What negative quantity is it? It's 0.97 minus 1. It's negative 0.03. As a percent, that's negative 3%. That is the relative rate of change per unit time. You could also describe it as a relative rate of decay without a negative sign. You could say the relative rate of decay is 3%. But since I'm using the word change instead of decay, I'm going to put a negative sign in there and say the relative rate of change is negative 3%. What about for g of t? Its growth factor, change factor, which is going to be the same as the growth factor, is this. In other words, it's growing. The relative rate of change is a positive number, and in fact, it is this number minus 1. So in each case, you subtract 1 to get 0.03045, and as a percent, that's 3.045%. Okay? So for every unit that t increases by one unit at a time, that's the percent growth in the function g of t. On to part E. Is the graph increasing or decreasing? F of t is decay. That's a decreasing graph. The graph looks like that. In fact, I'm going to answer part F as well here. E and F at the same time. That's what the graph looks like for exponential decay. It's decreasing. It's going down as t increases. It is called concave up because it looks like part of a smile, you might say. More officially, it's concave up because the slope, even though it's negative, is getting bigger. It's getting closer to 0. As negative numbers get closer to 0, they are getting bigger on a number line. They're moving to the right. These slopes that you see here of the graph start out kind of steep negative values, but they get closer to 0 as you move to the right. That means it's concave up. It looks like part of a smile. With the function g of t, we're doing again E and F. That function is exponential growth. The graph will end up looking like that. That's increasing. It's moving upward. Function values are going up as t increases. It is still concave up. It still looks like part of a smile. So both cases are concave up, whether you are decaying or growing. But with decay, you are a decreasing function, and with growth, you are an increasing function. This case, it's concave up. Yes, the slopes are increasing. They're positive this time. They are increasing. It's concave up. The last part, part G. For approximately what value of t in each case does the function output equal 6? Okay, I said in this video we're not doing logarithms. So to officially find the answer to that, you'd want to use logarithms. But here we will just use technology. We want to solve for when the function output equals 6. So in this case, we want to solve for 4.6, the first function here, f of t, 8.3 times 0.97 to the t power. I want to set that equal to 6. That word's supposed to say set here. Set that equal to 6 and solve for t. Solve for t. Okay, we're going to just do it with technology. We can graph this thing as a function of t. We can also graph a horizontal line at y equals 6 and see where they intersect. So we have the function is 8.3 times 0.97 to the t power, which of course in the calculator is going to be an x power. And we also want to graph the function y equals 6, and we want to see where these intersect. All right, this is decay, so it will be some positive value of x here. It's hard to say exactly how long it's going to take. We might try going out to 10 at first. The function value starts out at 8.3. Let's go up to 10 there as well. Let's see if we can see that these things intersect in this window or not. If not, we'll have to go out a little further. It looks like just barely. Oh, just barely. Better do it again here. Just barely. They almost intersect in the window. We can use the trace function to see where they intersect approximately. We can also use some sort of intersect function. We could do a calculation here. Go to my calculate menu up there and see where these intersect. the first curve and the second curve, and I guess it's close to 10, a little bit bigger than 10 maybe there. Looks like they intersect when x is about 10.65, so for in terms of t, that would be t is about 10.65. The other function is decay and starts out is growth and starts out at 4.6 and will grow to 6 at some positive time. So we want to solve 4.6 times e to the 0.03 t. When does that equal 6? I'm guessing that's probably going to be a little bit bigger window. Let's go back to my y equals screen here. 4.6 times e. E is right there above the ln on my calculator right there. To the 0.03 times x power. My window, let's go out a bit further. Let's try going to, say, 30 and see how this does here. We'll look at the graphs. There's the function. There's y equals 6. Okay, I didn't have to go out so far. Let's do my calculate menu for the intersection. First curve, second curve, and I guess still pretty close to 10, I guess. Oh, there's a little less than 10 this time, actually. About 8.86 is what it looks like, 8.86. T is about 8.86. Okay, so we can use technology. We can also use logarithms, but we're not there yet. That'll come in a video that will be coming pretty soon. Problem number 2, we've got, once again, an exponential function. This time we're calling the dependent variable p. P equals f of t equals p sub 0, which represents just one number. Some people call it p naught for short, times the base a to the t power. This is an exponential function. It's also sometimes written like this, p sub 0 times 1 plus r to the t, where evidently a equals 1 plus r, so r would equal a minus 1. A is the base. You could call it the change factor per unit time. R is the relative rate of change per unit time. When a is bigger than 1, r is positive, and when a is between 0 and 1, r is negative. We're given 2 data points. Suppose f of t is 42.9 and f of 5 is 53.4. 3 things to do. Find the base, a, find the relative rate of change, r, and find the initial value, p0 or p0 if you prefer. All right, it's always easy to find the initial value if you happen to know f of 0, but we don't know f of 0, so it's going to be a little trickier. How do you find a? It's a little bit unclear. If you plug in these numbers, you do get a system of 2 equations and 2 unknowns. F of 2 equals 42.9 means that when t is 2, p is 42.9, so I can plug those numbers into the equality between these 2 expressions and try to solve for ultimately 2 unknowns, the p sub 0 and the a. I could say, I'm going to switch the sides of these things, 42.9 is f of 2 is p sub 0 times a to the second power. F of 5 equaling 53.4 implies that 53.4 equals p sub 0 times a to the 5th power. So this is a system, a nonlinear system of 2 equations and 2 unknowns. In general, nonlinear systems of equations can be really hard to solve, maybe even you might say impossible. But this one is doable. It may not be clear how to do it, but it is doable. What you want to do is you actually want to divide one equation by the other. Say the bottom equation by the first equation, or vice versa. You can do it either way, because 2 really nice things are going to happen when you do that. The p sub 0s are going to divide out. P sub 0 divided by p sub 0 is 1. And with the a's, you'll be able to, well, subtract the exponents. Here's what I mean. Divide the second equation by the first. I can say that 53.4 divided by 42.9 equals p sub 0 times a to the 5th over p sub 0 times a to the 2nd power. And both sides simplify. This side simplifies with my calculator. The p sub 0s divide out to a 1, and you don't have to write them anymore. With the a's, you subtract the exponents. a to the 5th divided by a squared is a to the 5 minus 2 is a to the 3rd power. Okay, very nice. It simplifies very nice. With the left side, we can simplify that as well. 53.4 divided by 42.9 is about 1.244755. 1.244755. Okay, so that number equals a to the 3rd power. How do you solve such an equation for a? Take the cube root of both sides. That's what to do. A is going to be the cube root, approximately the cube root of 1.244755. But wait a minute, do we have a cube root function on our calculator? Well, maybe you do. I don't think I do. Well, maybe if I go to the catalog, I do. When you take the cube root of something, it's the same as raising it to the 1/3 power. And that'll be easier to do in the calculator. Raise this to the 1/3 power. I'll go ahead and use more decimal places like I have here in my calculator. Raise this to the 1/3 power. That's the same as the cube root. It's going to be a little closer to 1. You can see it's about 1.0757086. Okay, I'll go ahead and use that many decimal places. All right, there is your approximation for A. That's the answer to part A. That's the base. What about part B? Find the relative percent rate of change R. A is 1 plus R, therefore R is A minus 1. This is very easy. R is A minus 1. We did that in the first problem, this kind of thing. Take this number, subtract 1, you get approximately 0.0757086. This is often written as a percent, so move the decimal to the right 2 spots and write it as 7.75086%. Percent means per 100, so that's like taking this number and dividing by 100, which gives you this number. All right, that's the percent rate of change. That's how the percent that the growth is every 1 unit increase in time t. And part C, find the initial value p sub 0. Go back to the original system of equations and use either one of them. It doesn't matter, you should get the same thing. Solve for p0. I'll use the first one. p0 is going to be 42.9 divided by a squared. Okay, I took this equation and divided both sides by a squared. That's the a right there. Yep, okay. There's the thing that I need to square that, and then take 42.9 divided by that. P sub 0 looks to be about 37.074. 37.074. We could try to check the answer by using this equation instead. Let's go back to the A. The A was the 1.244755 to the 1/3 power. I'm using fewer decimal places here than before, so the answers will be off a little bit. I could hopefully get the same thing by taking 53.4 and dividing by a to the 5th power. I'm going to go ahead and raise this to the 5th power, and then take 53.4 and divide by that, and I should get the same answer for p sub 0 up to some rounding error. 37.074. Okay, it rounds the same thing to 3 places after the decimals we got before. Okay, so that is the initial value p0. Number 3, a deposit p sub 0 into a bank account has a doubling time, that's the key idea in this, of 20 years. What does that mean? It means no matter how much you put in the bank to start with, assuming your interest rate stays constant, which is not necessarily accurate, that's how long it takes your money to double. If you put $1,000 in, it'll double to $2,000 in 20 years. If you put $10,000 in, it'll double to $20,000 in 20 years. Doesn't matter if the interest rate stays constant, the doubling time will be constant. It does not depend on how much you deposit. Part A, how much bank will be in the bank account after 20 years, 40 years, 60 years, 80 years? Okay, this is what is the idea of a doubling time here. So after 20 years, well, the amount doubles. That's the doubling time. The initial deposit is p0. So it's going to be 2 times p0. If p0 was some specific number, again, like 10,000, this would be 20,000. But we can also think about this in the abstract. How about after 40 years? It's going to double again because another 20 years has gone by. Careful, what is that to? That's twice this, which is 4p0. Not 3p0, not 5, not 8. It's going to double again because another 20 years has gone by. After 60 years, it's going to double again because another 20 years has gone by to 8p0. And after 80 years, another 20 years has gone by, it's going to double again to 16 times p sub 0. So you got $10,000 and the doubling time is 20 years. That'll be 20,000, then 40,000, then 80,000, then 160,000. That's compound interest. That's exponential growth. The graph of your balance versus time is going to be increasing in concave up. It's ultimately going to grow very fast in the long run. Part B. Approximate the relative percent rate of growth per year. How do you do that? Okay, that's a little bit harder here. You need technology. The function representing your balance p as a function of time t could be written as in problem number 2 in the abstract in this form as an exponential function. It'll be exponential growth because a will have to be bigger than 1 because it's growing here. With decay, a is between 0 and 1. And instead of doubling time, you have something called a half-life. There is an alternative way to write this when you happen to know what the doubling time is. And that's to use a base of 2 and an exponent that's not just a t, but is t divided by the doubling time. T divided by 20. Okay, why does that work? Try values of t in it. If you replace t with 20, you get 2 to the 20 over 20, which is 2 to the first, which is 2. After 20 years, the balance is 2 times p0. After 40 years, if little t is 40, you get 40 over 20 up there in the exponent, which is 2. 2 squared is 4, just like you get a 4 there. After 60 years, 60 over 20 is 3. 2 cubed is 8, just like there's an 8 there. After 80 years, 80 over 20 is 4. 2 to the 4th is 16, just like there's a 16 there. It's a little trick to help you write the function. It's not in the exact same form as this, but it is equivalent. And we can figure out what the a is, and that'll help us solve part B by using a property of exponents. I can write this as 2 to the 1 over 20 power all to the t power. Why? Because to get from here to here, I would need to multiply those exponents. 1/20th times t is the same as t over 20. So again, just little tricks of the trade. Okay? So this really is the a. And then if I take that a and subtract 1 from it, that will be the r, that will be the relative rate of growth per year. Okay, that will be the answer. So use technology. 2 to the 1 over 20 power is the same as 2 to the 0.05. 1 over 20 is 0.05. So this becomes approximately p0 times 1.035265, say, to the t power. That's the a, which means the r is a minus 1 is approximately 0.035265, about 3.5265%. That's the relative rate of growth per year. You could also call it a relative rate of change per year because it is positive. Part C, approximate how much money is in the account after 50 years. Okay. Once again, we'll have to do that graphically. Oh, well, actually, we can just plug the numbers in, excuse me. So how much is in there after 50 years? I'd have to do it graphically with my calculator if I was solving for when will the account be, 100 times the starting amount or something. You can just find f of 50. And I can use this form if I like. P0 times 2 to the 50 over 20, which would be 2 to the 2.5 power. 2 to the 2.5 power is about 5.657. This is about 5.657 times p sub 0. Okay, that's how much is in there after 50 years. Again, if you had a particular number for p sub 0 like 10,000, then this would be 56,570 approximately. Let's double check that we get the same thing with this. Up to some rounding, 1.035265 to the 50th power. Yes, gives us about 5.657 again. Okay, as a confirmation of that we got the right answer. Number 4, a photocopy machine can reduce copies to 90% of their original size. By copying an already reduced copy, further reductions can be made. Part A. If a page is reduced to 90% of the original size, what percent enlargement is needed to return it to its original size? The answer is not 10%. That's the intuitive answer that people think is right. It's not exactly right. It's close to right, but not exactly. Percents are always relative to something, and that's the key thing. Maybe you know intuitively what to do. Is this your intuition? Maybe you know you should do 1 divided by 0.9 and then subtract 1 from that. The answer is about 11.11%. That is the answer. Could we justify that without intuition? Yeah, I could be official and write a function again. I could write p equals f of t equals p sub 0. Here p represents size, you might say. The base of the exponential function is 0.9, and it's going to get raised to the t power. That's what it means for the function to be, for the change factor to be 90%. This is exponential decay for every unit in time, which in this case time means number of copies you've made. The change factor is 0.9. You multiply the previous size by 0.9. That's what it means to be 90% of the original size. Okay? And we're trying to re-enlarge it back to its original size. Let's see here. So let's see, f of 0 is p sub 0, and f of 1 is p sub 0 times 0.9 p sub 0. What we really have to do is, and I hope this makes sense, I mean it's the same thing I just suggested to do intuitively, is to say the enlargement factor is f of 0 divided by f of 1. p0 times 0.9 times p0. The 0.9's cancel. I do 1 minus 1 over 0.9, which is 1.11 repeating, which means the percent enlargement would be 1.11 repeating minus 1, which would be 0.11 repeating, which would be about 11.11%. You know, if you're still feeling uncertain, you could pretend the original size has a certain area. You could pretend it's got an area of, say, 100 square centimeters or something, and multiply that by 0.9 to say that the reduced copy has an area of 90 square centimeters, and then ask, what do I need to multiply that by to get back to 100? If you multiply by 1.1, you don't get back to 100. You get to 99. You got to multiply by 1.1111 repeating to get back to 100. Okay? The growth factor has got to be 11.1 repeating percent to get back to the original amount. Part B. Estimate the number of times in succession the page must be copied to make the final copy less than 20% of the size of the original. Okay? Could solve this graphically. Could graph this function if I pick a particular value for p0 and see when it's back down to 20% of what it started with. Let's solve it in a non-graphical way. Let's just solve it by effectively iteration. So the first time you make the copy, it's 90% of the original size. And for every unit that t increases, where t here is not time release, it's number of copies, I need to keep multiplying by 0.9. So the second time it's 81% of the original. The third time it's 72.9% of the original. The fourth it's 65.61% of the original. That's the fourth time. I want to keep going until I'm less than 0.2. 5, 6, 7, 8, 9, 10, 11, 12, 13, getting close, 14, 15, doesn't quite do it, 16. Take 16 copies until I get less than 0.2, less than 20%. So 16 copies would be the answer. Our final problem for this video is not explicitly about exponential functions. It's more about understanding the relationships between numerical data for function outputs and the graphs, whether they are straight, concave up, or concave down. And to figure it out, what you want to do is you want to think about how the functions are changing as t, in this case, increases by 1 unit at a time. It is important that the t's are increasing by the same amount each time. It doesn't have to be 1 unit, it could be 3 units at a time, but it's got to be the same in each column here. What's the change in these functions as we go along? How do the functions change? So I'm drawing some arrows here to indicate that they are changing. They are all increasing, and these functions are all increasing. But by how much? Here, f of t increases by 1.1 right there, then 1.3 from 20.6 to 21.9, then 1.8, then looks like 2.2. Hard to see there. I'm saying it 2.2. F is increasing faster and faster as t increases by 1 unit at a time. That's indicative of it being concave up. This is f of t right there. The slope is getting larger and larger. The values are increasing faster and faster. Very important concepts for calculus. With g of t, each one of these changes, look at it carefully, is 1.1. 1.1, 1.1, 1.1, 1.1. That's a constant change in g. For constant increases in t of, in this case, 1 unit at a time, its outputs are increasing by 1.1 every time. That's indicative of linear growth in this case, straight line graph. This is g of t, which leaves this h of t. Does it fit? H is still growing, but by less and less each time. Here this change is 1.1, this change there is 0.8, then 0.6, then 0.4. The rate at which h is growing keeps decreasing. The slope of this graph keeps getting smaller and smaller. They're all positive slopes, but the way those positive slopes themselves change is different. Thanks for watching.